Today we're covering the first chapter of your Statistics 2 textbook. The chapter is called Hypothesis Testing. It's a new concept and slightly tricky, so I would like to explain it with the help of an example. Okay, so let's say there are a group of scientists who want to investigate whether toads prefer their right forelimbs over their left forelimbs. Okay, so now ordinarily one would imagine that toads use both their forelimbs equally. They don't have a preference of one or the other. But this bunch of scientists want to investigate whether that's not true, whether they prefer their right forelimbs. Okay, so what would they do to investigate this? The best way, of course, would be to get hold of all the toads in the world, figure out on an average whether they prefer their right forelimbs over their left, and then come to a conclusion. Now, that's not possible, right? Because there are a million toads in the world. So, as a scientist, what would you do? You'd take a sample of toads. So, let's say you took a sample of size 18. So, you took 18 toads randomly selected from the wild. And you conducted an experiment on them and figured out that 14 out of 18 preferred using their right forelimb. Now, if toads didn't have a preference, we would imagine that the result of this would be 9 out of 18. But since it's a random sample, you could end up with any kind of result, any value between 0 and 18. So, depending on the sample that you took, it's possible that you could get just 6 right-handed, right-limbed toads out of 18, or you could end up with 15 out of 18. You could end up with a whole range of values. However, in this particular sample, they got 14 out of 18. So now the question is this result statistically significant? So is the result of 14 by 18 statistically significant? What does this mean? This means that since I can't test uh, any more, maybe that's as much as I can do. I can only test 18 toads. Can I then extrapolate those results and then apply them to the entire population of toads and say all toads prefer, I mean, majority of toads prefer their right forelimb? Or can we use statistics to figure this out without actually catching a million toads and checking their limb preference? Okay, so hypothesis testing is when you have a theory and you can conduct a small experiment on a sample, but you want to check if the result that you got from that experiment, whether it is statistically significant, whether you can apply the result of that to the entire population and come to some conclusion. Okay, so that's what the hypothesis testing chapter is about. Right. So how do we check if our experimental result is statistically significant? For that, we use something called a null distribution. So the null distribution state is a distribution of the number of right-handed toads in an infinite number of 18 toad samples. So what this means is uh, the null distribution assumes that toads have no limb preference. Okay, it's likely that they prefer each limb identical to the other, and so what you would ideally like to do is you'll take an infinite number of samples and test the limb preference. So even if toads don't have a limb preference, Out of 18 toads in a sample, we're unlikely to always get 9, right? You could sometimes, depending on, because it's a random sample and depending where you took the sample from and what the toad happens to be doing, it's quite possible that you will end up with 8 out of 18 that are right limbed, or 15 out of 18 that are right. You'll get a whole set of values. If you plot them on a graph, they might look something like, the null distribution on a graph looks something like this, the normal distribution curve I've drawn here. Okay, so this is the null distribution curve. As you can see, the x-axis, which is the number of toads that favor their right forelimbs, is marked from 0 to 18. So out of a sample of 18, in some samples it might be 0, in some samples it may be as high as 18 out of 18, but a majority of the samples will give us number of right limb toads as around 9 as the mean value. Okay, so this is our null distribution. Now the null distribution is a binomial distribution. It's a distribution of the right forelimb toads, assuming that toads don't prefer any particular limb. So it's going to be x has a binomial distribution, sample size 18, and probability of the toad being right limbed is 0.5, right? Okay. So now we have to define our two hypotheses. The null hypothesis is that it's defined by the letter H naught. It is defined by the parameter probability of right-limbed toads is 0.5. And the scientist's hypothesis, which is the brand new hypothesis, is called H1. It's called the alternative hypothesis, and the alternative hypothesis is that probability of the toad being right-limbed is greater than 0.5. Okay. Now, what do we do? How do we check the statistical significance? We calculate the probability of x being the same as our experimental value of 14 by 18 or better than it. So probability, I've drawn it here in, marked it in red. On our null distribution, if the toads had no preference of limbs, what are the chances that we'll end up with a value of 14 out of 18 or better than 14 out of 18? So 15, 16, 17 and 18 out of 18. Okay. If this probability value, shown shaded in red, is high, then we can say that the result that we got of 14 out of 18 is probably statistically insignificant, because if you randomly choose a sample of 18 toads, you could very well get the same result. Okay, it's not hard to get a 14 out of 18. Whereas if this calculation on the null distribution gives us a low probability, then we can say that the result that we got in our experiment, 14 out of 18, is unusual enough to be statistically significant, right? Okay, so what is the probability value against which we test the significance? That is called the significance level, or alpha, and it's usually set at the beginning of the experiment. We say, if it is greater than, if the test statistic is greater than 5% or 2% or whatever, and in that case we will say that it's too high, and therefore your alternate hypothesis is statistically not significant. Okay, so this probability that we calculate is called the p-value. And if the p-value is greater than alpha, then we keep the null hypothesis. We'll say, you know what, it's easy to get 14 out of 18. There's a good chance that if we randomly select unbiased toads, we will still end up with a number like 14 out of 18 or better. And so we'll keep the null hypothesis, and there's no evidence to support or insufficient evidence to support the alternative hypothesis proposed by the scientists. On the other hand, if the p-value that you get is less than alpha, then we reject the null hypothesis and we can say there is evidence or there is sufficient evidence to suggest that toads prefer their right limbs. All right. So that's how we carry out a hypothesis test. I'm going to quickly go over the information again. So in hypothesis testing, we are testing a new hypothesis proposed by somebody. Okay, in this case, in this particular example, we had scientists propose the theory that toads prefer their right forelimbs over their left forelimbs. In order to test this theory, they took a sample of just 18 toads out of the million toads available in the world and tested them for limb preference and found that 14 out of 18 preferred their right forelimbs. Then the scientists asked the question, is this result that we got statistically significant? In order to test this significance, since they can't measure forelimb preference for all toads and they can just do it for this one sample, what they do is they use something called a null distribution. Now, what is a null distribution? A null distribution is if you assume that many 18 toad samples were randomly chosen and the number of right-handed toads was recorded, it is expected that, and under the assumption that toads don't prefer any limb, in which case you are likely to get a series of values for number of right-handed toads between 0 and 18. In some samples, you would have got 0 or 2 or 3. In others, you would have got 14, 15, 16 or whatever, even 18. But a majority of the samples will tell you that 9 out of 18 toads are right-limbed. So the x-axis on this null distribution is the number of toads favoring their right forelimbs, and the distribution used here is a binomial distribution, sample size 18 and probability 0.5, because with the null distribution we are talking about what is usually expected to be true, that toads do not favor any particular limb. Okay, so the two hypotheses are written explicitly like this in terms of some parameter. So the null hypothesis H0, we've written it as probability of toads preferring their right limb is 0.5. That means there's no preference of one limb over the other. And the scientist's new proposal or hypothesis is the alternative hypothesis, which says that the probability is greater than 0.5. Now, what you do is, on your null distribution, you calculate the probability that if toads had no preference, what are the chances of getting a result of 14 out of 18, which was our experimental result. And we also check for results better than that. So 15, 16, 17 and 18 out of 18, which is this whole red shaded section. Now, if that probability is very high, then we can say that the result that the scientists got is not that uncommon, and therefore it is not statistically significant. Whereas if it's unlikely in a bunch of random samples to get a result as good as 14 out of 18 or better, then we can say that what we found is statistically significant. So that is what this calculation is, probability of x greater than or equal to 14, because we're testing for the experimental result, which was 14, or anything better than that. and what you end up with is a p-value. You check the p-value against a predetermined significance level, which is usually within 10%. So 1%, 2%, these are the values that we usually set. So the significance level is considered to be high enough. So if the probability, if the p-value or this area in red, um, if that probability is greater than the significance level, then we're going to say that we're going to keep the null hypothesis. There's no evidence to support the alternative hypothesis. On the other hand, if the p-value is less than the significance level, then we can reject the null hypothesis because there's sufficient evidence to suggest that toads prefer their right limbs.